Hey, this is Miss Logan. Today I'll be talking about forces, free body diagrams, and how to find the net force on an object. Okay, so a force is a push or pull on an object, and we measure this in newtons, and it is also a vector. So it always needs a direction. So there are two main types of forces. The first one is a contact force, so two objects are touching each other, or there's added distance force, like gravity. So there are about 7 forces that we will go over. Now there may be additional forces that we have different names for. However, here are the big 7 that we focus on. So first is friction force, and this is force exerted when an object moves across something else. Okay, so most of the time it is opposite of the movement. Second, we have tension, and this is when we have a force through a rope or string. Now the biggest thing about this is it pulls equally on the object on both sides. Next we have normal force. I think a better name for this is called support force. So this is when we have an object that is on another object. Now the other big thing with normal force is it is always perpendicular to the surface of an object. And in a moment we'll see what that means. Next we have air resistance. So this is actually a type of friction. So this acts on an object when it is traveling through the air. So once again, it is most of the time opposite of the motion. Next we have applied force, which is kind of a little bit more general, but this is a force applied to an object by a person or another object. Then we have spring force, which we'll look at later in this unit what the equation is for. And this is a force exerted by a compressed or stretched spring. Last, we have gravity. This is the force that is always attracting an object down. And this is our only added distance force that we'll talk about in this unit. So one of the most important things in this chapter, in this unit, is to look at free body diagrams. And I often just call them FBDs. So they are a vector diagram that shows all the forces acting on an object. Because of this, they need to include all the forces acting on an object. What's also important in this is the size of the arrow matters. So as we go through the rest of this lesson, that's something that you should be noting as I go through different examples. Alright, so just brief instructions for how to go about this, and then we'll practice it. So for free body diagrams, you need to create a box or circle or just some shape to represent the object. You shouldn't be redrawing it and taking a lot of time to make it look really nice. It's just simply a vector diagram. Then you need to go through all the forces and think about, is it present? One thing you always know though is gravity is always present and it's down. So basically every problem you already have one. And if the force is present, you need to create an arrow and a direction to represent it. Like I said, the amount of arrow, so how long it is, does make a difference, and we'll see that in a minute. Okay, so let's do some free body diagram practice. For the first example, a car sits in a parking lot. So I'm just going to draw my car. One thing I know that is present is my force of gravity. Now, if I go through my other forces, this car is sitting on something else, so we're going to have force normal. Now, you'll notice that both of my arrows are the same shape and size, and that's because this object is sitting still. Everything is equal to 0. Next one, a ball is thrown straight up into the air. I'm going to draw my ball. We know that I have force of gravity down. And going up, I have to have applied force. Now, I might also have air resistance if it was noted in the problem. Next, a box is pushed across the floor by 2 friends. So I know I have force of gravity, and because this box is sitting on something else, I also have force normal. But I have another force as well. This is being moved, so I'm going to have force applied. I could also have friction going back the other way. Now, something you'll note right here is that my 2 arrows are different sizes. So my force applied is much larger than my force of friction. That's because my force applied is actually moving. And last one, a box is sitting on a ramp. So I have my box. I have force of gravity going straight down. However, I also have my force normal, and if we look back at our notes, force normal is perpendicular to the surface. So it's actually going at an angle. Pretty cool. This problem, I could also have friction that's going back, and those are my only forces. All right, so net force is the total force on an object. So there's different ways that we can look at this, and we're going to kind of look at it through free body diagrams. So if we look at this one to the right, we'll see that I have force of gravity, force normal, force applied, and force of friction. Now we'll see all the arrows are the same size. This is important because this means my net force equals 0. If we look below this, we'll see I have 5 going to the right and 5 going to the left. So I have 5 newtons minus 5 newtons, so my total force is 0. Last over in this example, I have these two guys are carrying the couch, one with 25 newtons to the right and 20 newtons. So that's total 45 newtons. Now it's important for net force that we're always thinking about our directions. Positive to the right, negative to the left, positive up, and negative. So when we're looking at forces, we have to think about which direction are they going, and if I need to add or subtract them. We have two situations with net force. Our first situation is when an object is at rest or at constant velocity. And this means our net force is equal to 0. So this is just like this example in my free body diagram that I showed. I have equal forces in all directions, okay? Or I have, my second situation is that an object is accelerating. So my next net force equals ma. So that's force equals mass times acceleration. So in this case right here, it looks like all my forces are equal. However, if my force of friction is 1 newton and my force applied is 3 newtons, then I have a net force of 2 newtons. So that means that my objects will be accelerating. Okay, so let's just go through an example problem. So a 10 kilogram box is pushed with 10 newtons to the right, and friction pushes back with a force of 4 newtons. What is the acceleration on the box? So first, let's get started by making a free body diagram. So my mass is equal to 10 kg, and my box is being pushed 10 newtons to the right and 4 newtons to the left. Now, I know that this is accelerating, so I need to use my net force is equal to mass times acceleration. Now, what's my net force? I cannot add these two together, so this is not correct. Why can't I add these two together? Well, 10 newtons is going to the right positive, and 4 newtons is going to the left negative. So instead, I'm going to have 10 minus 4, which will give me a net force of 6 newtons. All right, so let's solve for acceleration. So I have force net over m equals a. Here I can plug in my numbers. So 6 newtons over 10. That'll give me acceleration of 0.6 meters per second squared. So make sure you've taken notes for this lesson and you complete the Google form.